E trazendo mais uma palestra para vocês, falando sobre Introduction to Container Security, o Cloud Computing Technologist and Evangelist at Red Hat, Thomas Cameron. Come on, Thomas. Thank you.
Good afternoon, everybody. As you can tell, I'm afraid I don't speak Portuguese, and I apologize for that, so you'll have to listen to my English. My name is Thomas Cameron, and I am a Senior Principal Technical Marketing Manager at Red Hat. I am a technologist. I'm a Red Hat Certified Architect, and have been doing this for about 23 years now, so I've been in the industry for a while. My contact information is up there, and you can follow me on Twitter. I would love to have you keep up with me there. I post a lot of information about containers and security and general IT news. First off, thank you very much for having me. I'm very honored to be here. I love São Paulo, and so it's fantastic for me to be here. When I left home in Texas, it was about 43 or 44 degrees. So I came here and I was like, so it's wonderful to be here. I appreciate you being here, and Red Hat appreciates the opportunity to sponsor this Openstack Day. So we're glad to be here. We're glad you're here, and we owe you a debt of honor, of gratitude for you supporting the community and for letting us be part of the community. So thank you. What we'll be talking about today is a little bit of an introduction about containers, what they are, where they came from, what Red Hat has done with containers, how containers work, what containers are not, and then what makes up container security. We'll talk about kernel namespaces, control groups, the daemon itself, Linux kernel capabilities, my favorite topic, security enhanced Linux. Everybody loves security enhanced Linux, right? Oh, come on! Some tips and tricks, and then some conclusions. So first off, as I said, Thomas Cameron, I've been doing this since 1993, so I've been in the industry for a long time. One of the reasons that I love security is I was actually a police officer before I changed careers and became a technologist. So I really love forensics and computer security. I know it's a strange story. Ask me at the bar later, we'll talk about it. I've been at Red Hat since 2005. I am a Red Hat Certified Architect, and in the past I was a Microsoft guy. Before that I was a Novell guy. I know, I'm old, right? I had to shave the beard because it was so gray. I spent a lot of time focusing on security in organizations like banks and financial services places, manufacturing, e-commerce, and so on. I do not claim to know everything about container security, but I've been doing this long enough that I have some very impressive scars. So Red Hat has been working on containers since before 2010. We acquired a company called Makara to buy a platform as a service solution. That was renamed or rebranded OpenShift. We used cartridges with SE Linux and Linux control groups, kernel namespaces, and so on. But as happens in open source communities, the Docker project and the company actually became so popular that we realized it made sense for us to start contributing to Docker. So we've been working with Docker, and now we're working with Cryo and other technologies to have a more standard container format without proprietary lock-in. We started participating in 2003, and the last time I checked, I think we were the #2 contributor to upstream Docker, so we do a lot of work there. Now, industry adoption of containerization is incredible. The companies that are on board, Apsara, Cisco, EMC, Fujitsu, Goldman Sachs, blah, 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 even Microsoft is working with container standardization, which is awesome. I mean, because I was like, not too sure. But now it's amazing seeing the things that's coming out of Microsoft. So it's amazing. So what are containers? Containerization is just a technology to abstract and isolate application services from the underlying operating system. We can get incredible density. You can put a whole lot more applications on a machine than you can virtual machines. So there are many, many benefits to containerization. And the same container can run on multiple platforms. You can run an Ubuntu container on Fedora or a CentOS container on Red Hat Enterprise Linux. It's very, very portable. We've been promised write once, run anywhere for a long time. I think containers are pretty much there. So what are containers not? Well, they're not the answer to everything. They're good for a lot of things. They are not the cure to all that ails you, and they're not fit for every application yet. We're getting there. And they're not virtualization, obviously. You can run containers on bare metal, and it works just fine. Now, what are the components that make up container security? There are actually many things that make up container security, both in and outside of the operating system, and we'll talk about those. The first is namespaces, kernel namespaces. Namespaces are just a way to make a global resource, like mounts and process IDs, Unix time sharing, inter-process communication, network namespaces, and user namespaces, to be segregated and controlled so that they look to be unique on a per process basis, and I'll show you more of that in a minute. Mount namespaces are just a collection of file system mounts that make up the process view of the file system hierarchy. The root of a container is made up of the files packaged by the container author. So when you build a container, you'll define what the file system looks like inside. Other mounts are added via mount points through that mount namespace for security and also for convenience. And we do some things like mount proc so that the container can see the process table inside of the container but not outside. PTMX so the container can spawn their own isolated terminals. Some locations like proc kcore are masked over with dev null because you don't want the container to see the kernel core space on the host. That would be a bad thing. And some, some locations like procsys are made read-only so that it's, because the sysfs is not completely virtualized. So if you look, I'm running an Ubuntu container on my Red Hat Enterprise Linux machine, and you see that when I run the mount command, I see the root file system, and the container just thinks it's a root file system, but you see the huge mapping, the Docker mapping right there. The same thing is true for proc and tempfs and devpts and msq and sysfs. These are just ways that the container thinks that it is alone and that its own machine. So that gives you better security, so you can't, because it can't access the host unless you grant it access, which we'll talk about later. Process ID namespaces just isolate process IDs so that, again, the container thinks that all of the processes inside of the container are the only processes on the system. So if I do a Docker run a Fedora bash instance, for instance, sorry. So when I do a PS command, it sees bash as process ID 1, which we all know is silly, right? Because that's systemd usually. But if I then do a PSAX on the host that's running the container, there's my Docker run. It's actually 18.557. So that namespace just isolates so that the container does not know about what's going on the host. The same is true of user namespaces. They isolate user IDs and group IDs so that inside of the container, it appears that there are only the users that are defined by the author of the container. This is very useful for multi-tenancy, and you can grant root privileges inside of the container without giving them access to the outside of the container on the host. So I used OCI tools here to look at the UUID mappings, or UID mappings, I'm sorry. So you see that this is where we virtualize that UID inside of the container so that it thinks it's 0 without having root privileges on the host. Network namespaces, same thing. This is just a way for the container to have its own IP address without having to be configured, and this all happens sort of automatically under the hood. In this case, I ran a Fedora instance, and then I run docker inspect against it, and it's got an address that doesn't appear on my laptop or on my host anywhere. It's a private address inside of the container so that you can manage networking within your container space. I mean, my laptop doesn't even have an IP address associated with it, so it's just sitting on my desk. Inter-process communication namespaces, same thing, but with IPCs. If I look inside of the container with no applications running, there are no inter-process communications, where if I look on my laptop that I wrote this on, of course there are dozens or hundreds of them. And Unix time-sharing namespaces, basically it lets the container think it's a separate OS, its own identity, its own host name, and own domain name. So on my laptop, I run the hostname command, and you can see that it's my T540, but then inside of the container when I run hostname, it's a randomly generated string. So again, the container thinks it's its own operating system with no other operating system above it. Now, Linux control groups are a way to aggregate and partition tasks. So all of their children, any forks or execs, all live within that same same control group. And that allows us to have fine-grained control over things like CPU, disk, network, memory. The whole system can be carved up into small pieces for both security and control. So even if a container is compromised, or if somebody writes a bad application that runs out of control and hammers that container, the host is not affected, and the other containers on the host are not affected either. So when I run the command system control status docker.service, I get the control group and slice information. So you can see there are that's my control group, and you can see that everything in the Docker service and underneath it will be in its own set of control groups, and then we can carve up processes underneath more finely and have better control over it. You can navigate the sysfs cgroup sudo directory to see what resources are allocated. Now, there are thousands of them. I'm not going to go into all of them. But you can see the control group information about everything that's happening in your system, including the Docker process and all the child processes. So as an example, I create a container with 100 megs of memory. So I do Docker run, and I give it 100 megs of memory, and just run bash. And you can see there's performance counters, the freezer, CPU accounting, block I/O for disk access, memory, process IDs, CPU sets, et cetera, et cetera, et cetera. So these are all examples of all the control groups that are being used within the container to segregate workloads and to control them. And if I look at inside of the container, if I look at the memory limit in bytes, you see there's my 100 megabytes times 1024. So you can see that that's the amount of memory. That container only thinks it has 100 megs of memory. It's very fine-grained control. Now, another example of what's really cool about control groups is I'm going to create a container with 10 megs of memory, which is silly, but it makes a really good example. I create that container with 10 megs of memory. I run bash, and then I fork bomb it, right? Because every year in university, computer science students learn about fork bombing, and they think they're really clever. And so then they go and they do it on your systems. Well, with this, you run the system out of memory, it crashes, and when you look in the log file, you see that the out-of-memory killer kicks off, and it shuts the machine down. And you can see the control group that's affected. So this is one of the neat things, and one of the security features is control groups can also stop a badly behaved container from hurting the host or hurting other systems. The container daemon itself, right now it's Docker, eventually it'll be something more community-minded, is responsible for managing the control groups, orchestrating the namespaces, and so on. And because of this, you need to be very careful about the way that you grant privileges to run the Docker daemon or run containers. It runs with root privileges, and you got to be aware of that. So some common sense rules, right? Don't let just anyone run Docker. The Docker documentation recommends that you add users to the Docker group. We don't do that. We actually set it up so that you have to be a root user or a root equivalent user. So you have to use su or sudo to do any of the Docker commands. Like starting and stopping the daemon is what I'm talking about. Now, if you're using the REST API, make sure it's up to date. Make sure it's protected by SSL or TLS. Don't allow unencrypted communications to go across your network. It's just common sense for any sort of network-facing application. The next thing that I want to talk about is Linux kernel capabilities. And this is a really neat function, libcap, that allows you to put fine-grained controls over users and what system calls they can call. Historically, if I have root on the machine, I could do anything that I want. If I have root inside of a container, I could do anything that I want. But with libcap, you can do things like say, I'm not going to allow you to make changes to networking. I'm not going to allow you to run the netbind service capability. I'm not going to allow you to access a port under 1024. And so the default list for Linux capabilities is a very minimal list. So when a container comes up, it has a very minimal, the least privileges that it needs to be able to run. And we limit, the community limits what service or what system calls can be called. And then cap sysadmin, which is sort of the catch-all for all of the privileges that don't fit anywhere else, is also dropped. So containers, in containers, a lot of the capabilities to manage network and other services are not really needed. They get handled by the daemon. So SSH services, cron, file system mounts and unmounts, you don't need to do that from within the container. That should be defined at instantiation time. So we disable those. And by default, Docker disallows many root capabilities, including the ability to modify logs, change networking, kernel memory, time, and so on. And you can actually read, you can go to GitHub and look inside of Docker to see what the utilities, what the capabilities are and what are limited in there. You can look at the source code. SE Linux. I love SE Linux. I love SE Linux because I used to hate SE Linux. And I forced myself to present on SE Linux and to learn it well enough to where I now appreciate it, and I think that it's a fantastic set of tools. SE Linux is a mandatory access control system. Processes and files and memories and network interfaces, everything is labeled. And there is an administrative policy that is fixed. You can't make changes unless you have root on the host. And you can even lock that down if you want to be really, really mean to the sysadmin. And those policies will determine how processes can interact with files, with each other, with network ports, and so on. So SE Linux is primarily concerned with labeling and with type enforcement. So if you have a service, let's just call it the foo service. The executable on disk might have the label foo exec type. The startup scripts might have foo config type. The log files might be foo log type, and the data might be foo data type. So when foo is running, the process in memory might just have the label foo_t or foo type. Type enforcement is the set of rules that says that when a process running in the foo type context tries to access a file on the file system with a label maybe foo config type or foo data type, that's allowed. That makes sense, right? You want the foo service to be able to access the config files and to access the data. But when that process, foo, with a label foo type, tries to write to a log file, or when it tries to write to a log file, that would be allowed as well. That makes sense. But any other access, unless it is explicitly allowed, will be denied. So if the foo process running in the foo type context tries to access /home/t Cameron, for instance, with the label user home dir, even if the permissions on that directory are 777, don't do that. But even if the permissions are wide open, SE Linux will step in and say, nope, not allowed. SE Linux labels are stored as extended attributes on the file system, or they're stored in memory when the system boots up. SE Linux labels are stored in the context, the SE Linux user, the role, the type, and then multi-level security label and multi-category security label. So for the mythical foo service, the full syntax might be user u, object role, foo type, and then MLS S0 and MCS S0. And that's important, and we'll look at that more in a little bit. The default policy for SE Linux in RPM-based distros like Fedora and Red Hat Enterprise Linux and so on is targeted. In the targeted policy, we don't use the SE Linux user or role, so we can ignore those. And we can also ignore the MLS label since that's only used for the MLS policy, like top secret versus secret in the military or in intelligence. We really only care about the type. Remember that this is type enforcement. And the MCS label is extra identifiers. SE Linux for containers called svert not svert. I just drew a complete blank. I'll come back to that. We can be very granular about what the processes are and how they access other processes. So even though these are almost completely identical, user U, object role, foo type, S0, but that C0 versus C1 means that for SE Linux, they are completely different. For us, they're easy to read, but for SE Linux, they're completely different. So type enforcement says that a process with the first label is different from a process with the second, so the policy would prevent them from interacting. And there's no policy allowing a process running with those labels to access the file system unless it's labeled foo config type or foo content type. And neither of those processes would be allowed to access, for instance, Etsy shadow, because it has the Etsy shadow type, or the label shadow_t. Now, on standalone systems, if you're just running containerization on standalone systems, all of the containers run in the same context by default. If you use OpenShift, for instance, which is our container management platform, every container runs in a separate SE Linux context. So, you know, you've got all of these different machines that are running in context, C0, C1, C2, C3, C4, C5, and so on. So even if somebody compromises one container and then they use it to attack other containers, SE Linux should block that access. So we have very fine-grained control using SE Linux. I'm going to emulate an exploit here. So I'm going to pretend like I got in as somebody has taken over a container. So what I do is you'll notice that when I run ID, I am 0 and 0. I am I am the root user, so I have total control. And you can see that my type is unconfined, and I have access from C0 to C1023. I use the runcon command to run in the context of OpenShift, and I give myself C0, C1, which is as if I were running as a single container on an OpenShift environment, on a Kubernetes type of environment. And I run the command bash/bin/bash. And immediately, I can't even access my home bashrc file. When I look at Etsy Shadow, permission denied because I'm in the wrong SE Linux context. I try to create a file, permission denied. I try to look in the home directories of users, permission denied. And so I'm thinking, well, maybe because I'm root, I can just turn SE Linux off. But even when I try to run set and force 0, because I am no longer in the correct SE Linux context, it's denied. So this is an example of what happens if even as root, somebody accesses a container and tries to attack the host or other containers on the machine. So again, I love SE Linux. It's ugly and it's difficult, but once you learn it, it is incredibly powerful. Seccomp is just a way of doing syscall filtering, and we're getting out of time, so I'm going to move very quickly. So you can stop system calls, and the way that it works is, let me just show you an example. You create a JSON file, and I can say for the system call get CWD, I'm going to throw an error. Now what happens is I run docker run IT, and I say security ops seccomp equals that default JSON file. I run busybox, and the first thing that happens is I have an error message. So if I do pwd, print working directory, that calls get CWD, and I get an error message. So you can even get more granular when you start up containers by using seccomp. Seccomp is really awesome, and it's just JSON. It's not difficult to code. So some tips and tricks. Containers, at the end of the day, are just fancy processes with fancy files running on your host. So if you keep that in mind, just use common sense, right? Have a process in place to update your containers and follow it. You have to update your containers. Run services in the containers with the lowest privilege possible and drop privileges as soon as you can. Drop root privileges as soon as you can. If you have to access the file system on the host, mount it read-only unless there's a good reason not to. Treat root inside the container just like you would root on the host, and watch your log files. We've done a lot of work, both Red Hat and the upstream community have done a lot of work to make logging useful. And enable no new privileges for your container if it's appropriate, so that somebody can't do a privilege escalation inside of the container. Don't, hey, I found this container on the internet. I'm going to bring it into my enterprise and run it. What could possibly go wrong? Don't run SSH inside of your container. Seriously, stop it. Don't run with root privileges unless you absolutely have to. Don't disable SE Linux. Do you hear me? Okay. And this one is actually, what? This one's actually very common. I see this a lot. Don't have a developer build a container, hand it off to operations, and then walk away. If you're going to build containers, build your CI/CD pipeline. Always get updates. Go out to Git. Have something that's automatically going to update. Because it's real easy. We all get in hurries, right? We're all very busy. Raise your hand if you're not busy. Exactly. We're all very busy, and it's easy to take the easy way out and go, oh, I'm just going to build it and put it out there. You've got to have a plan, and you've got to follow that plan for keeping your containers up to date. And don't run production containers on unsupported platforms. Hey, I built this thing that I downloaded from the internet. Don't do that. So, in conclusion, I love containerization. We can get application density that's unheard of. You can get agility, and you can push workloads into production faster than almost any other technology that I can think of. And they leverage some incredible capabilities on the Linux kernel. So if you already know Linux, this stuff is already there, and you don't even have to do very much with it. By design, they're relatively secure, but there are some rules for security. Just like every other piece of software out there, use common sense. Container technology requires some care and maintenance. If they're well maintained, containers can make your business more agile, less complex, and absolutely safe if they're done right. Whew, I made it with like 15 seconds over. Thank you very much for being here. Thank you very much for letting me talk to you today. If you have any questions, I'm Thomas at redhat.com or Thomas D. Cameron on Twitter. Thank you.